Hello APC Mechanics students in Unit 4 System of Particles and Linear Momentum, Class 4, 4.2 Impulse and Momentum, Part 2. Then in today's video we're gonna solve some exercises. Exercise 1, a block of mass m is sliding to the left with speed v0 on a horizontal frictionless surface. At t0, a horizontal time-dependent force F is applied to the block. Force F is directed to the right and its magnitude is given by the formula F is bt squared, where b is a constant coefficient. How long would it take for the block to acquire the velocity v0 directed to the right? So what's happening here is that the block initially is moving to the left. Suddenly, at the instant t is equal to 0, a force that depends on time, and this is important, we will elaborate now why, is applied to the block, and suddenly the block will start to lose speed, and finally it will have a speed v0 directed now to the right. So why it is important to clarify that the force depends on time? Because we know force might depends on two factors. Whenever we're talking it depends on time, then most probably we're talking about impulse, and if it depends on or we say it's related to position, then we're talking about the work done by the force. Now, knowing that the final velocity is v0 to the right and the initial velocity is v0 to the left, then we know the change in momentum, and then change in momentum is equal to the impulse, which is the integral of the force over a time interval from t is equal to 0 to capital T, as indicated here. So how long we need to find the capital or the final time. So we're gonna say that the impulse is given by the change in momentum on one hand, which is equal to mv final. Let me do it this way. P final minus P initial, mv final minus mv initial. Now v final is mv0 to the right, and v initial would be minus v0, because remember that this is a velocity, so that would be the double of mv0. And on the other hand, the impulse can be written as integral from 0 to capital T. So remember that we're interested in determining capital T for f dt. Now we know explicitly f is given by bt squared, so 0 to capital T bt squared dt. B is a constant, can be dragged out. Now the integral of quadratic would be cubic from 0 to capital T. Now here we will compute this once at capital T and once at 0. You can ignore the 0, that would be bt cube over 3. So these then are equal to each other. Then bt cube over 3 is equal to the double of mv0. We're interested in finding t. Then in this case t cube would be given by 6 mv0 divided by b, and now we can perform the cubic root, so which is 6 mv0 divided by b. Right? Now exercise 2, before I refer to the question, look at the graph. It's symmetric, so we're either interested in the slope or the area under the curve. We have f versus t, so area would give us the change in momentum or the impulse. Indeed, we're interested in the change from momentum from 0 to 4. Notice that this is positive area that cancels with the negative area, then the change in the momentum is 0. Now exercise 3, we have the mass with the force sensor attached starting from rest. The force sensor exerts a force on the card to speed it up. The graph above shows the force F exerted by the sensor on the card as function of time. We need the change in momentum. Now this is an ft graph, then the change in momentum, which is delta p, is equal to the area under the curve. Now here this is basically hard to divide it into shapes like triangle, rectangle, or whatever. Now we will proceed with the following trick. We will count the number of grids found under this curve, and this is basically, we're using estimation, and we will see which one is the closest to that. Now this is a complete grid, so we have 1 plus. Now basically let's assume this with these Let me see. Alright, would give us 2. Another one. Now basically this part with this uncompleted grid would give us another one. Let me say this with that would complete to 1. And let me assume this is more or less like half. Okay. Then that would be almost 4.5. So we have 4.5 grids. Now what is the area of each grid? Each grid corresponds to a length of 2 newtons and the width of 1 second. So the area of one grid would be 2 times 1, which is basically 2 newton second. Then here what we're gonna do is 4.5 times 2, and that would be almost 9 newton seconds, and the closest answer to this would be 8.5 newton second. Exercise for the net force F acting on an object that moves along a straight line is given as function of time. So whenever the function is explicitly given as function of time, it means we're interested in the change in momentum or the impulse given by kappa t square plus tau, where kappa is 1 newton per second square and tau is 1 newton. We need to find the change in momentum from 0 to 3 seconds. It's as function of time, then we need to realize it as an integral. Then delta p would be given by the integral from 0 to 3 of f dt, which is integral from 0 to 3 of kappa is given by 1, tau is given by 1, so t square plus 1 multiplied by dt, and that would be t cubed divided by 3 plus t. From 0 to 3 you can ignore the 0, that would be 3 cubed divided by 3 plus 3. Plugging that on the calculator, or let me do it quickly, that would be 3 square plus 3, which is 12 basically, and the unit of delta p is kilogram meter per second, and the correct answer would be C. Exercise 5. The graph above shows a variable force F that acts on an object as it moves along a straight line as function of time. What is the change in momentum of the object from 2 seconds to 4 seconds? Then we can determine the area under the curve from 2 to 4 seconds, since it's an FT curve. Now we can divide this into 2 shapes, a rectangle or a square. So this is the first one, A1, and that would be the second one, which is basically A2. So A1 would be given by what? By length times width. Now the length is 2, the width is 2, and that would be 4 newton seconds. The area A2 would be half base times height, which is basically half the base is 2, the height is 2 also, and that would be 2 newton seconds. So if I add up the two areas, that would be 60 newtons per second, which is also equivalent to 6 kilogram meter per second, which makes C to be the correct answer. And here let me also solve it using a second method. Now what is the second method? We know that the change in momentum can be determined as an integral from 2 to 4 of f dt. True? Now, but we don't know the function of f explicitly. However, it's given as a straight line, and we know that the equation of straight line passing through the origin is given by f, which is the slope, multiplied by t. Now the slope here in this case is given by what we can choose 2 points. This is the first point, which is the origin 0, 0, and the second point would be 1 seconds, 1 newton. Then the slope would be 1 minus 0 over 1 minus 0, and that would be 1 newtons per second, right? Okay, so f would be given by just 1 multiplied by t, which is basically t. Then f is given by the function, which is t. And now we can replace this in the integral, and we can say that that would be the integral from 2 to 4 of t dt. That would be t squared divided by 2 from 2 to 4, and that would be 4 square over 2 minus 2 square over 2, which is basically 16 over 2, 8, minus 2, and that would be again 6 kilogram meter per second, which makes D to be also the correct answer. Exercise 6, this is a bit tricky. A 0.5 kilogram rubber ball initially moves with a speed of 10 meters per second in the positive x direction toward a stationary wall as shown above. The ball bounces back of the wall with a speed of 5 meters per second in the negative x direction. Which of the following best represents the rate of change of the ball's momentum? So basically, according to Newton's second law, F is given by dp by dt. So we need to identify the graphical representation of the force. This is an easier way to think about the problem. Which force? The force exerted by the wall on the ball itself, because this is the only force exerted on the ball along the direction of motion, which is the positive x direction. I was thinking about the pull of gravity, but the pull of gravity acts vertically, so we can ignore it for the moment. We are only interested along the direction of the motion of the ball. Now all right, so this is basically initial, and that would be final, because initially it's moving to the right, then finally it's moving to the left. It's moving in the positive x direction initially. So before it hit the wall, there is no contact between the ball and the wall, so initially the force exerted is being 0. And after it changes its direction and moves to the left, also the force is 0. So our force initially and finally should start with 0 and end with 0, which makes either A to be correct or B to be correct, and making C, D, and E to be wrong. This is 1. 2. The force exerted by the wall on the ball, which represents the change in momentum of the ball, is in the negative direction, because, and the biggest proof on that, the ball has changed direction and it's moving to the left, which makes B to be the correct one. Now exercise 7, an object is moving in a straight line along the x-axis. The momentum of the object px as a function of time is shown in the graph above. Which statement below correctly describes the net force that the object experiences during the time period shown? So we know that the net force is given by the change in momentum. Now according to this formula, which is Newton's second law, which means that F is the slope of a PT graph. The slope here in this case, it's a constant because it's a straight line, it's negative, which makes D to be the correct answer. The momentum P of a moving object as function of time is given by the expression P is kt cube, where k is a constant. The force causing the motion is given by the expression, so we know that according to Newton's second law, F is dp by dt, which can be utilized as an operator of kt cube, and that would be 3kt square, which makes A to be the correct answer. If one knows only the constant resultant force acting on an object and the time during which the force acts, so we know the force, we know the time, so we can determine the change in the momentum of the object, which is equal to the impulse. Now a space shuttle has a mass, we have the inertia. In order to stay in circular orbit, it must have a velocity given by 8,000. The pilot discovers that the shuttle has slowed down to 7,900 and the shuttle speed needs to increase. In order to increase the speed, we need to provide an impulse, basically, which is a force over a time interval. If the thrusters exerts a constant force, we have the force. How long? So how long we need to find time. So to exert this force in order to return to the shuttle to the orbital velocity. So because the force is constant, we can use the fact that delta P is given by F delta T. Why? Because the impulse, which is delta P, that can be written as an integral from t1 to t2 of f dt. Now if f is constant, it can be dragged out, and the integral from t1 to t2 dt, and in this case this is just 1, then that would be a linear t2 minus t1, and that would be delta t. So in brief, we can say that delta p equals f delta t in two cases: if f is constant, or we're talking about the average force. And we're interested in finding delta t. Delta t would be given by delta p divided by f. We know the value of f, which is given by 50,000. Now it's left to find delta p, which is the mass, or let me say p2 minus p1. p2 is mv2 minus mv1 divided by 50,000. Let me factor out the mass, which is given by 90,000, and that would be V2 minus V1 over 50,000. Now that would be 90,000 times the change in velocity. Now the change in velocity that is required is only 100, because this is 8,000 and this is 7,900. So times 100, or you can do it explicitly to be 8,000, and that would be 7,900 divided by 50,000. So we cancel the zeros, and that would be 900 divided by 5, and the answer would be 180 seconds, and the correct answer would be D. In an experiment, students use a force sensor to apply a force of magnitude F to an object of mass that is initially at rest. The force is exerted in the positive x direction for a time t is equal to capital T. The impulse exerted on this device is J. Which of the following procedure changes would result in an impulse 2J being exerted on an object? So whenever we see 2J, then we're thinking about the factor of change. Now we know that J, if you're thinking about the average, would be given by, or even the integral form from T1 to T2 of f dt. Now if f is halved, then J will halve, which makes this is wrong. Now if this is halved and this is doubled, so doubling T here and halving this would be J the same. Now f stays the same and the time is doubled, so this is correct. Let me check the other. So this is doubled and this is doubled, that would be quadrupled, so this is wrong. This is doubled and this is halved, which makes this wrong. And now exercise 12. This is an interesting exercise. An object is moving in a straight line along the x-axis. The net force Fx exerted on the object as function of time t is shown on the graph. Which of the following could be the momentum px of the object as function of time? So we're interested in relating the momentum to the force. The only equation we know at this point is given by F is dp by dt. Now we have two choices to approach the problem. Either we try from the ft graph to check which one is correct, or do it the other way around. We try to analyze the choice based on the given. So, and this is easier because f is given by dp by dt, which means that f is the slope. So we're gonna analyze the slope in each case. Now here, for the first part, the force should be constant, which directly makes this to be wrong, because the force is not constant here, it's increasing. Moreover, here if you look carefully, the force is 0 because the slope is 0. Here the force again is constant, so this doesn't agree with this one. And similarly here, f is what? Constant. F is 0 and f is constant because it's straight line, and we know that the slope of a straight line is 0. Here f is not constant, it's increasing, here it's decreasing. So here let me say that f increases, f is constant, and f is decreasing to make things easier. Now here in the first part, from point 1 to point 2, almost the curve appears to be a straight line, so we expect that f should be constant. Then here momentarily at this point, f should be 0. And for the other part, we expect that f also should be constant and negative, which doesn't agree with this. Now here in this case, the slope, if you do these sketches, you notice that f should decrease because the slope is decreasing, and then f should remain constant as an approximation for this line, and here again f should increase, which doesn't agree with this. As for the last choice, which will be correct, if you notice carefully here, the slope is increasing, so the first part f increases, then partly it becomes constant, then it would decrease again. Now the net force on a particle as function of time is given by the equation F is 6 kt square, where k is a positive constant in units of Newton per second square. Which of the following could represent the change in the momentum delta p as function of time? We know that delta p can be related to the force via an integral from 0 to t of f dt, and that would be integral from 0 to t 6 kt square. 6k is a constant, can be dragged out, that would be 0 to t squared dt, and that would be 6k t cubed divided by 3, and t can be replaced simply by t. 6 over 3, that would be 2kt cube, which makes D to be the correct answer. Exercise 14, we have the mass, we have the initial speed before, strikes a tennis racket and rebounds at 10 meters per second. We have lost some speed and we're moving in the opposite direction due to an impulse exerted by the racket on the ball. And this happens in a time of 0.03 seconds. What's the magnitude of the average force? Average force, then we're safe to use F is given by delta P by delta T. Remember that F comes in two flavors, F to be dP by dt and delta P by delta T. We use this one whenever we're talking about the average force, and that would be, we factor out the mass, V2 minus V1 divided by the duration. The mass is given by 0.06. The final velocity should be minus 10 because it's moving in the negative direction, minus the initial velocity, which is plus 15, minus with plus give us minus, over 0.03, and that would give us minus 50 newtons. And notice that all the answers are correct, and indeed they're asking us for the magnitude, which makes E to be the correct answer. A block on a level horizontal surface of negligible friction is initially traveling at 20 meters per second to the left. A horizontal force F is exerted to the right on the block for the time interval. The magnitude of the force is given by the as function of time to be alpha t, where alpha is 240. What is the magnitude of the change in momentum of the block due to the horizontal force? Then the change in momentum is given by delta P, which is integral from the initial instant, which is 0 to 0.1 of F dt, and the force F is given by alpha t. Alpha is given by 240, then 240t. 240 can be dragged out. That would be the integral from 0 to 0.1 of t dt. So that would be 240 t squared divided by 2, which is 120, computed from 0 to 0.1. You can ignore the 0.1 square, and that would be 1.2 kilogram meter per second, which makes A to be the correct answer. Now notice that here they mentioned that initially it's traveling at 20 meters per second, but we never used it in our calculation, and that's fine. This is a common thing in AP. Now, which of the following is equivalent to unit of momentum? Momentum has two units, which is given by kilogram meter per second, which is equal to Newton second, which makes D to be the correct answer. Exercise 17 as an exit ticket for today's video. The graph of velocity as function of time shown above is for 10 kg box moving along the x-axis. Based on the graph, which of the following is a true statement? Now, the linear momentum of the box is constant over the entire frame. No, momentum is related to velocity. If velocity is constant, momentum is constant. Velocity changes, so A is wrong. The linear momentum of the box is only constant between 2 and 5. Yeah, this is perfectly true, because from 2 to 5, this is a horizontal line dictating the velocity, which makes it constant, which means that P is constant. Then that's it for me in this video, guys. See you soon in a new one.